Okay, so our equations now are, we have the continuity equation intact. And now I just have the viscous terms. So let me write y square term first. Right, and then I have my pressure drop term equal to -1, where I've taken the 1 to the other side. And then similarly for the v direction, I'm now going to multiply throughout by 1 over lambda. Sorry. So because I multiply throughout by 1 over lambda, I get a 1 by lambda squared equals to 0. And then I should write down the boundary conditions. So I know that u equals v equals 0 at y is equal to half plus epsilon by 2 sine 2 pi x. And then I have dou u by dou y equals v equals 0 at y equals 0. Okay, so let's pause for a moment to appreciate the form of these equations and what solving them would entail. So it is useful whenever you are working on a transport problem to take time to understand the structure of the problem, the mathematical equations, and to try and walk through in your mind whether you have equal number of equations and equal number of unknowns, and to try and understand how different terms of the equation would have to be dealt with in a solution, either numerical or analytical. And we shall do this throughout this problem, and you will see that doing this periodically helps us manage the overall calculation, which otherwise might seem to be overwhelmingly long. And by breaking it into pieces and keeping track of what each stage is supposed to do, it becomes easier to think of the calculation and to also make sure that we don't make errors. Alright, so looking at these equations now, this is the first time in this course that we are actually dealing with a 2D problem. And so they seem to be relatively complex, maybe more complicated than anything you've looked at earlier in your transport courses. And that's to be expected, right? Because these equations are supposed to be able, or will be able certainly, to capture the flow in any arbitrary wavy geometry. So the geometry could be only slightly wavy, a small departure from flat. That's what would happen if epsilon is small. But it could be a situation also, because right now we have made no approximation on epsilon. It could be a situation where it's extremely wavy, right? So we could be looking at something that's just got slight waviness relative to the channel depth, where it almost is flat. Or you could be looking at a situation where it is extremely wavy, right, where the idea of it approaching flat plates is absurd. And yet both these situations, right, the very wavy one and the slightly wavy one, are going to be described by the same equations. So in the case of extreme waviness, it's clearly going to be a strongly two-dimensional flow. And so it does now, you would expect the equations to have some more complexity than the simple case of flow between flat plates. Now at the same time, so given that, if you look at the structure of the equations, you see that you have one equation, you have basically three unknowns, u, v, and the pressure. and you have three equations, so that seems fine. The equations for u and v are second order in y, and you have corresponding two boundary conditions each in the y direction. Now in the x direction, you see that you're also second order in the x direction, but you don't have yet any boundary conditions there. But we could, so there are two ways of looking at this. One is we could specify boundary conditions, at the inlet and the outlet. Another way of specifying boundary conditions is to say that we're going to seek solutions far from the inlet, where we expect the velocity field to also be periodic, given that the walls themselves are periodic. So although I have not written down boundary conditions for x, basically I do have boundary conditions, because I'm going to seek, I'm going to look for a solution that's valid far from the entrance of the channel, where we expect the velocity field to also be periodic in x, with a wavelength that it makes sense to be equal to that of capital L, or some multiple of L in general. But here we'll see that being a simple linear problem, it just takes on the periodicity of the boundary. So we do have boundary conditions in x, they are just periodic boundary conditions with wavelength L. Or in this case, with wavelength 1 in the x direction, since we've scaled the problem. Alright, so that takes care of the boundary conditions. Now, this problem will show us the importance of pressure in the case of incompressible flows, because you see that you have one equation. You can think of the u momentum equation, this equation here, as being an equation that gives you u, that determines u if only you knew the pressure gradient in the x direction. Similarly for v. But then you have this unknown pressures left, and the reason they exist is that this pressure field is what will allow u and v, or force u and v, to satisfy the continuity equation. Another way to think about this problem, which will be particularly useful in the perturbation, domain perturbation method that we're going to use, is to say that, let's say I somehow know the value of the pressure gradient in the x direction. I already know the dominant contribution to the pressure gradient. Let's say I also know the deviations of the pressure gradient due to the waviness of the wall. Then I can solve for u. From that, I can then obtain v from the continuity equation. And once I know v, I can complete the calculation of the pressure gradient of the pressure field by solving for pressure using the v momentum equation. So this shows you more clearly how the pressures can be used to enforce velocity continuity. So in either case, you see that we have a well-posed problem here, and with different possible ways of solving this problem, let's say numerically, if we were doing it for general values of epsilon. Also, we have another parameter that we haven't commented about yet much, that's the aspect ratio lambda. So its variation basically means that we could be looking at problems like this, where the waviness is relatively slow in the x direction, or in other words, where lambda is close to 1 or much less than 1. If it's much, if lambda is much, the way I've defined it, if lambda is much less than 1, it means the wavelength is much greater than the depth, right? So it's something like this, but with an even longer wavelength. But if lambda is very large, then you could be looking at something like a sinusoidal variation, which I can't draw very well here, but something very choppy, which comes closer to mimicking roughness, right? Or we could be looking at something very lazy, which may be more like what you would see in a structured microchannel or an engineered surface. In either case, we are not going to make any assumption of on lambda here. We will treat the problem for arbitrary lambda, which means we can cover both these cases. But we will require that the amplitude of the waviness, which is epsilon, is going to be small. And that's what will allow us to use a domain perturbation. There's another possible approximation to make, which is to say that let epsilon be arbitrary, which would correspond to this case, right, where I have small amplitude or large amplitude, but I require lambda to be small, which means that I'm looking at very lazy waves on the surface of the wall. You can see this could also be a perturbation parameter, because for small lambda, I would essentially get a simpler equation in the u direction, At leading order, if I multiply throughout by lambda square, you see that at leading order here for small lambda, I get just that the pressure gradient in the y direction is 0, and there is no vertical velocity component coming into the equation, and I could then solve for just the u equation of momentum and then calculate for v from the continuity equation. This in fact is what is known as a lubrication approximation, which comes up whenever we have slow variations of the boundary geometry along the flow direction. That's equivalent to saying that I'm going to do a perturbation solution in the parameter lambda, but allowing the amplitude to be arbitrarily large. That limit of the problem we will look at later on in this course when we take up the perturbation approximation in a systematic way. And in fact, we will see that it's a very useful idea in a whole range of interesting problems. But in today's course, we are not going to look at that limit. Rather, we are going to take the case of arbitrary wavelength, but require the amplitude to be small, as that is the case which is amenable to the domain perturbation method. Since the domain perturbation method works if you can identify a simple boundary shape that is very close to or asymptotically close to the more complicated domain of interest. And that would be guaranteed if epsilon is small, because you can see that if epsilon tends to 0, we basically tend to a boundary located at y equal to half, which would be flow between half and minus half, which would be flow between flat plates. So let's now approach the problem through domain perturbation. But first let me label these equations, which are the ones we're actually going to be solving, as 1a, 1b, and 1c. Okay, so to understand the idea of domain perturbation, let us first zoom into what's actually going on near one of the wavy walls, let's say the top wavy wall. So here is my waviness. There is fluid flowing along the wall, so you can imagine the streamlines would look something like this, right near the top wall. So that's my wall, which I am trying to hash, not very successfully, but nevertheless it will suffice. Alright, so my velocity field now, both u and v, clearly are going to be functions of x, y, and the parameter epsilon, which defines the depth of this or the amplitude of this waviness. And as I said, as epsilon varies, the solutions will vary because the domain on which they are being solved is itself varying. Ultimately, where if epsilon is 0, I am going to get straight fully developed flow with straight streamlines. Now, the mean width, the mean position of this wall I am going to indicate by this dashed line. This corresponds to y equal to half, whereas at the waviness of the wall, y is actually equal to h of x, which is half the non-dimensional h of x, which is half plus epsilon by 2 sine 2 pi x. Alright, okay, so the idea now is the following, that if epsilon is small, it means basically the deviations of the real boundary from this flat surface y equal to half is going to be small. So the idea behind this is, can I replace the deflected wall or the wavy wall, which is only a small deviation away from the flat surface, by the flat boundary, but at the same time, so can I make that replacement provided I am able to identify a modified boundary condition applicable at the flat surface, which nevertheless allows me to approximately satisfy the true boundary conditions on the wavy surface. Right, so what I want is, I want a new boundary condition applicable at y equal to half that allows u and v to approximately satisfy the true boundary conditions at y equal to h of x. So it's h of x comma epsilon really, of course, right? For small epsilon. So this is what I'm really after and at the core of the domain perturbation method. And the idea, the key idea that allows us to try and identify this boundary condition is to think of the velocity field as a mathematical function, which it is, that strictly speaking has been solved for and is defined only on the domain. That means the fields u and v, the mathematical functions u and v, are supposed to be defined from y equal to minus h to y equal to plus h. Right? And their values are supposed to go to 0 at this wall. So just focusing on the top wall, u, for example, is a mathematical function which becomes 0 at this wall. However, suppose I was to continue and evaluate that function. I don't know the solution for this function, but we expect the function to be smooth and continuous, in other words, analytic. And so if this function is smooth and continuous and has some well-defined mathematical form, which I don't know yet, if I choose to evaluate this function beyond the wall, I'm not going to suddenly get infinity because the function is varying smoothly. Instead, I will get some value, but presumably I'll get, for example, a negative value. So if u is positive everywhere as it's supposed to be because the flow is in the x direction, it becomes 0 at the wall, and if I evaluate it beyond the wall, I will still get some well-defined value for u, but it may be negative. And that negative value of u beyond the wall has no physical meaning, but nevertheless, as a mathematical function, it can be continued, so to speak, beyond the wall y equal to h of x. This idea is called analytic continuation, which is valid for all smooth continuous functions or analytic functions. It's not valid, of course, for weird functions that have discontinuities, let's say at a boundary surface, because then if I go beyond the boundary, the function may be infinity or not defined. Just not definable. But in this problem where we are going to have a smooth function, we can always continue the function. Another way to think of this is, even if I don't know the value, the mathematical form of the function, so to speak, so that I can simply evaluate it beyond the boundary, I can always extrapolate and identify to arbitrary accuracy the value of u beyond the wall by using a Taylor series, right? So I can write the value of u at any position, let's say here outside the wall. So let's call this position a, right? So y equal to a. So I can evaluate u at y equal to a in terms of u at y equal to h using the Taylor series approximation. So u at y equal to a is going to be basically in the Taylor series u at y equal to h plus the derivative of u with respect to y evaluated at h times y minus h and so on to higher order terms. And so if I know all the derivatives, so if the function u is smooth and continuous and it has all derivatives well defined, and if I know all those derivatives at the wall, I can then use a Taylor series to find the value of u beyond the wall. But now the number of Taylor series terms I require is going to depend, for good accuracy, is going to depend on how far I am from the wall, right? That's the idea of the Taylor series. And so if I'm close to the wall, maybe only one or two terms of this Taylor series is sufficient. And the closest to the wall here is really related to epsilon. So if epsilon is small, I can rewrite the values of y at the wall in terms of the values at the flat surface y equal to half in terms of a Taylor series, even though for some portions of the wall y equal to half actually exists outside the wall. Right? This should not trouble us because of the idea of analytic continuation. So what I'm going to do is, when I say replace the boundary condition at y equal to half by boundary condition at y equal to h by y equal to half, what I'm really going to do is rewrite the fields at y equal to h in terms of its value at y equal to half using a Taylor series, and then substitute that into the boundary condition, and that will automatically give me an approximate boundary condition where all the terms are evaluated at y equal to half. And the number of Taylor series terms I will need to make this boundary condition approximately valid is really going to depend on the value of epsilon. So if epsilon is small, I will need just a few terms. Okay, so with that idea in mind, let's now write down the equations and things will immediately become clear. So let's start with the no-slip equation for u. So I know the true boundary condition is u at h of x is equal to 0, right? Which basically means u at half plus epsilon times sine 2 pi x by 2 is equal to 0. Right? This is just epsilon. So now if I use a Taylor series expansion for u about y equal to half, which basically means about epsilon equal to 0. So I do the Taylor series expansion really in terms of epsilon, you might say. So it's an expansion in y, but the deviation in the y variable I'm interested in is basically epsilon, right? Okay, and then also with the idea of analytic continuation in mind, I can replace this term by u at y equals half plus dou u by dou y evaluated at y equals half times the deviation of the y location from half, which I am interested in, which is nothing but epsilon sine 2 pi x by 2. This is basically delta y. So it's du by dy delta y evaluated at the starting point y equal to half, but that's equivalent to saying evaluating this derivative at epsilon equals 0. But I'll just write it as y equal to half for the moment. And then I can take yet another order. Again evaluated at y equals half, but this time, so of course I have a 1 by 2 factor here, so it's 1 by 2 dou square u by dou y square at y equal to half times epsilon square by 2 square, which is 4 sine square of 2 pi x. Right, so it's the delta y the whole square. And the 1 by 2 factor comes from the Taylor series, right? Plus, now really it's order of epsilon cube terms and higher, which I'm going to neglect for now, equals 0. So what this shows you is that, yes, so what we have now is we have started with the no-slip condition, we've used the Taylor series, and we've now obtained an equation which is a condition on the field u, but everywhere evaluated at y equal to half, which has the form of a power series expansion in epsilon. So now you see automatically that instead of solving the problem on the Wavy-Wall domain by using the Taylor series expansion or the domain perturbation type approach, we replace that problem by another approximate problem that is valid on the domain between flat walls, where the boundary conditions are applied at y equal to half, but it's a different boundary condition from the original one. It's now a power series in epsilon. So we've effectively moved the dependence of the problem on epsilon from being inside the domain of the problem, right? Which means that u was earlier evaluated at h of x, where it's actually h of x comma epsilon. So the epsilon dependence of the problem was locked in the location of the boundary condition. We have removed that dependency on epsilon from the location of the boundary condition into the boundary condition itself, leaving the boundary condition now a constant flat value y equal to half. So that is the utility of this domain perturbation method, which basically, or which can be thought of as a Taylor series expansion of the boundary condition for small values of epsilon. Because only then is the true boundary located a short distance away from the so-called base domain boundary, or the domain perturbation problems boundary. Okay, so this is the heart of the idea, and because we now have a perturbation, a power series form, asymptotic power series form for my boundary condition, it will make sense to just go ahead and write down, to assume that we can obtain a power series solution, perturbation solution for the fields u and v themselves, and the rest of the method will then proceed like the usual perturbation method. So the heart of the domain perturbation method lies in how we replace the boundary conditions in terms of approximate power series boundary conditions, and then the rest of the method is essentially the same old perturbation series solution ideas. So then I can seek a perturbation solution in the usual way. So U is U naught, the base solution, which will be flow between flat plates, because when epsilon is 0, I just have U at y equal to half equals 0. Similarly for V. Of course, I haven't written it down here, but I have an identical equation for V equals, for the no slip condition on V at y equal to half, and then the two conditions, symmetry conditions at y equal to 0 remain unchanged, because they are not being perturbed at all with epsilon. So that is one benefit of replacing the bottom boundary condition with a symmetry condition, but it's purely algebraic convenience, just to make our calculation simpler. You could write a similar boundary condition at the bottom wall with just negative signs, just y equal to minus half here. Alright, so the solution I seek now will be U is U naught, which is of course a function of x and y, but not epsilon, right? Because epsilon's dependency is in the power series itself. Plus epsilon square U2 of x comma y. And higher order terms. Similarly for V, right, so the boundary conditions, so the dependence of V on epsilon is only its no slip boundary condition at the Wavy-Wall, which has the same form as what we've written here for U. The domain equations in this case, of course, have no epsilon dependence, so you'll get the same domain equations for U and V at every order in epsilon. So the only thing that's going to change is the boundary conditions on each problem, which is again something slightly different from what you have seen before, where the boundary conditions are sort of simple, and it's the domain equations that change at different orders. And yes, we're not done yet, because of course we have a third unknown, which is the pressure field, right? So since only the gradients of pressure, of course, are important in this incompressible problem, I'll directly expand the gradients of pressure. And as I said, since these are deviations about the constant pressure gradient case, and I know that if epsilon is 0, I'm basically going to get, I should get the solution where the pressure gradient is just plus 1 here. So I know that these pressure gradients dp dx, dp dy are all order epsilon, right? Because they will go to 0 if epsilon is 0. So I can directly write that this is epsilon. Let's call it g1 as a function of x comma y, the unknown pressure gradient in x. And similarly in the y direction. Right, so that so this sets up, I mean, these are our perturbation expansions. And now what's left to us is, of course, to substitute these expansions into our governing equations, obtain and the boundary and the domain perturbation form of the boundary condition, of course, and obtain problems, sequential problems at each order, and solve them sequentially, like we have been doing in our earlier cases of perturbation problems. However, before we begin actually solving the problem, it's useful to consider how one could evaluate the flow rate of the fluid through this wavy-wall channel. So one question of potential interest when we consider such problems as far as the flow field is concerned is not just the flow pattern, which we can get from getting the approximate solutions of the fields, but an integrated quantity of interest would be the flow rate. So now normally we'll calculate the non-dimensional flow rate by integrating the u component of velocity from y equal to minus h to plus h. But now in this case we are going to get a perturbed solution which is valid only from y equal to minus half to plus half. So it's important to be able to obtain an expression for the flow rate, not in terms of an integration over the wavy domain, but as an integration over the flat wall domain, but suitably accounting for the domain perturbation nature of those approximate solutions. So let's see how that can be done, and it's useful to do it at this stage because it will help us also with the solution of our problem, and also because it's one quantity that's of immediate interest, sort of integrated quantity of interest, which one might want to know as a function of the aspect ratio lambda, for example.